Hello, everyone, and welcome to today's webinar, Precision Sectioning Redefined, Bringing Ultramicrotomy to the Digital Age. I am Cassie Saltman of LabRoots, and I'll be your moderator for today's event. Today's educational web seminar is presented by LabRoots and brought to you by Leica Microsystems. To learn more, visit www.leica-microsystems.com. We encourage you to participate today by submitting any questions you may have during the presentation. To do so, simply type them into the Ask a Question box and click Submit. We'll answer as many questions as we have time for at the end of the presentation. Also, if you're experiencing any technical issues, you can utilize this Q&A box and we will assist you directly. I'd like to now welcome our speaker, Jan de Bock, Application Manager, Leica Microsystems. Jan, you may now begin your presentation.
Thank you so much for this kind introduction. I'm very happy and proud to present to you today the UC Annuity, Leica Microsystems' latest innovation in the field of ultramicrotomy. Many of you might know the UC6 and UC7 and the latest big step, the ARTOS 3D towards array tomography applications. All of these innovations based on the experience and the feedback of you as our customers and of course over the last decades. And nevertheless, we also learned that we have users working on the machines every day and being experts, blindly managing to get perfect sections. But there's also a huge group of users which do not regularly perform ultramicrotomy. That's why we are frequently asked to provide trainings to keep the knowledge and expertise in these labs up. To overcome these needs and to support inexperienced users, Leica Microsystems decided to bring ultramicrotomy to the digital age. Here you can see the UC Annuity. This is an advanced room temperature configuration. And we provide to you two stereo microscope options, bright field and what is new, fluorescence illumination. A camera, which is used for automatic functions and image analysis to provide these automatic functions. A touchscreen control here with intuitive user interface. One single base unit, which can be upgraded in multiple ways. And most importantly, we can provide to you a motorized segment arc and a motorized knife block, which provides to you automatic functions, helping inexperienced users to be more effective and working more reliably on the machine. Here you can see how the segment arc and the sample rotation can be set very precisely and automatically. Also the knife arc, hence the knife angle, can be controlled automatically and very precisely. Here you can see the knife arc moving, opening up in the angle. And these three integrated motors are the basis for many automatic applications supporting you as a user. Well, the typical order of a workflow in ultramicrotomy is trimming the sample towards a perfect block face. Sectioning, of course, here you can see the sections in the boat of the knife. And of course, pick up of the sections onto a EM grid. All of these steps have their typical obstacles, but in particular during the pickup, the pressure is high as it's the last step and the loss of the section is even more painful. But how can we make the pickup more easy? That is typically done by working with the lines of sections here on the right-hand side, so-called ribbons. Like this, the single sections are not floating around as the sections are attached to each other, and the manipulation is more easily done and safe. In addition, together with a consistent pickup, of course, we get a 3D information of the sample by the order of these sections. But how do we get perfect ribbons? Well, one precondition is to create a well-trimmed block face with parallel edges. You can see it here on the left-hand side, perfectly parallel edges. In particular, the leading edge, the low edge here, and the upper edge. Of course, there are many experts around in labs and facilities who can do this. But this exactly needs their time and can lead to bottlenecks in getting the science done. Here on the right-hand side, you see I drew these lines to show you the edges, the lower and the upper edge here in this ribbon. With the automatic trimming function of the UC and UET, we can now kind of democratize this function. Here in this video, I would like to show you how the auto trimming is performed. We mount the sample here, trimming knife, a 45 degrees trimming knife. And within the software of the UC and UET, you can see the auto trimming module. We first set the start and the end, meaning the cutting window, and then the different parameters for our block face and the machine are appearing. The knife width, which type of knife we are using, the block face size, the block face trim depth, and the trim depth at the sides, at the edges, which is given here now with 80 microns, but we can change it throughout the workflow. First, we set the knife width. Here it's 2531. Of course, you can measure it, and we give in also the 45 degrees inclined angle of the knife. Now we define the right side of the block face, and you see here in the camera image how the knife is moving to the right-hand side by moving here by rolling this east-west button. This is now the right-hand edge of our block face at 0 degrees. By clicking next, we define the side trim depth. How deep is this edge? 80 microns. And we set the block face width in this direction, which is 400 micrometer. It does not need to be a square, but it can also be a rectangle, of course. Here on the left-hand side, you see the camera image. I was measuring a little bit what 400 micrometers is. Then the sample is turning automatically 90 degrees, and we now define the lower edge of the block face by moving the knife to the according position and setting again the block face height in this case, not the width, but the height. The sample is turning automatically backwards 90 degrees, and then we move below the cutting window, and the start button down here becomes green, and we start. Now the trimming process is, of course, fastened a little bit. It takes about 1 minute for each of these sides, depending on how deep you go. This is now the front face cutting. Now the right side of the block face at 0 degrees. Then the knife is retracting, as you can see here, moving to the left side and cutting away the left side of the block face. Going deep 80 microns now. Then the beauty is you can walk away. Actually, the system is doing this automatically. It turns now the sample 90 degrees and starts to cut the right side, trim the right-hand side at 90 degrees turned, and now the left side 90 degrees turned, being the lower edge. Sample is turning back again, and this is done automatically, so you don't need to stay with the machine. The process is finished. Let's have a look now where and how our block face is looking alike. And if you zoom in, you can see the perfect block face here, 45-degree edges, 80 microns deep, 400 by 400 micrometers width and height. So I showed you how the automation empowers yourself and your team. The UC and UET handles the trimming for you. All you need is to define the boundaries of your sample block and walk away. all users with a minimal amount of training can now create perfect block faces, and therefore creating the precondition for perfect ribbons. Now, of course, after the trimming, the sectioning follows, and for the sectioning, the alignment between knife and our perfect block face now is crucial. And the first critical step is to set the knife angle correctly parallel to the block face. Here in this top view, you can see that the knife needs to be rotated towards the block face, that it's parallel to the block face. And if this is not the case, the knife or the sample can be damaged. Secondly, the edges, or better, the the leading edge here has to be parallel to the knife blade. And this is done by correcting the sample rotation. And again, sample damage or loss can happen if this is not done perfectly. And of course, if this line here is not really parallel, the edges of the block face, the sections do not adhere, and we cannot create ribbons. Last but not least, the sample tilt here from the side view has to be checked to not create any damage or sample loss. Damage in particular to the knife, because if the knife is running here into the sample, this can be damaged. As one can see, it's not trivial to do the alignment, especially for inexperienced users. With the automatic alignment function of the UC and UAT, this is now a thing of the past. So how does this work? Here we load the knife and the sample is already mounted, and then you just click Auto Alignment. You can then see some pre-requirements which must be fulfilled, and you just click Start here. You can see a center line in the camera image, and then feedback lines are appearing, showing the edges of the sample and the knife, and the system is performing now exactly what I was talking about, checking the knife angle, checking the sample rotation and the sample tilt. The video is a little bit unfastened. It takes up to 3-4 minutes for the alignment in general. You can see the knife angle is checked, and now the sample rotation iteration is performed, measuring the angle between the sample and the knife. And then as a last step, the sample tilt is checked. And as we do manually, we move the sample along the knife to check the height of the light gap. And this is done automatically here. And then you have the choice to finish now with the distance between sample and knife, or you can approach. And here in this case, we have chosen to approach to the sample. Now we see there's a specific distance kept. And then the last step could be that we move manually towards the sample, as I did it here. And when a bluish line is appearing, we know that we are in the range of something like 400 nanometers close to the sample. I did this here until I saw a bluish line. And of course, you could then fine align the last tiny steps. Maybe here you can see that the bluish line is appearing, and we are a little bit closer here than on this side, because here it's more bluish than on the other side. Then we fill the boat and can adjust the water level with the reflexomat. And of course, the idea is that we have as less partial sections as possible. Just here the eccentricity, and press Start. You see the full sections appearing. And then it's done. Now, as shown, there's a reduced need for user training thanks to the outer alignment, and we can simplify the sectioning process, making it more efficient and user-friendly. Now, in the previous section, I was not talking much about the front face trimming to get the sample, to get to the sample in the depth of the block. But in line with volume imaging, it's more and more important to reach a specific target plane inside of the block effectively. Now, if you look at this sample here, this is provided by Viola and Ines from the Schwab team at EMBL. You can see that there's a lot of resin above the actual target sample here. This is a Platinereis worm, and we have to get rid of this resin above the sample to really reach the target plane. Now we could do semi-thin sections with toluidine blue and cut also away a little bit of the sample, because as soon as you see it, you already have lost a little bit of your sample. But this is time consuming, and you have to also transfer between the ultramicrotome and the microscope. On the other hand, you could also use the focused ion beam on the SEM, but again, this is time consuming and the beam time is very expensive. And you're also limited in trimming size in XY. So with the UCN Unity now, it's possible to load X-ray 3D data, so-called microcomputer tomography data, or in short, micro-CT data. And now we can interactively determine the target plane and approach the target plane in a controlled, fast, and safe way. And I want to specifically thank the Yannick Schwab team to develop this on basis of their crosshair software. So how does this work? You need your sample, of course, a trimming knife, and the pre-recorded micro-CT data must be available. And then here we see the sample with the lava, with the Platinereis lava. And then you can automatically align your sample to the knife, or the knife to the sample. I showed to you this before, so we can click. You can go to the next step. And we load the 3D auto trim software. Here is the 3D volume, the micro-CT data, which was pre-recorded, and it can be loaded into the UCN Unity software. And you can interactively now turn the micro-CT data volume here to find the correct target plane. But first we have to align the micro-CT data to the actual sample block. This is done by defining the top surface on the left-hand side, and on the right-hand side, we move these marker points to the top surface of the sample in the micro-CT data. Then we mark the corners to have them as reference to our actual sample, which is mounted on the ultramicrotome. And of course, these corners have to be now correctly top left, top right, bottom left, bottom right. And then the most crucial step is to define the target plane where the front face is cut, the front face target plane. And you can adjust the height and the pitch, the jaw of this plane. And in this case here, we wanted to cut off the little head of the Platinereis lava. Fine adjust, zoom in, and then we do the sample rotation, which should fit to your needs. You can see the little red angle, the little red arrow here, which is turning and shows you the cutting direction. As a last step, you can define a little margin, 5 micrometer before the knife stops before the target plane. Then you press adjust, and the system is automatically calculating the knife angle, the sample tilt, and the sample rotation according to the needs of your target plane. Then you can start the trimming. Sample is automatically trimmed, and as you can see, we succeeded in cutting away the top head here of the lava, shown here in this post-trimming micro-CT dataset. Turning it around, you can see that the head is cut away, giving you the effective time to directly go to the target volume. So I showed you that you can reach deep targets with ease. You can interactively program the block face creation site and automatically trim it to reach the plane of interest. This helps you to really effectively start the 3D volume acquisition on the electron microscope directly where it matters. Besides using micro-CT data, it's also possible to selectively target structures by fluorescence. Here you can see on the left-hand side a nice fluorescence image of nematode worms, C. elegans worms, kindly provided by Professor Thorsten Hoppe from the Institute for Genetics in Cologne. And a very warm thank you to Felix Gerdke, who helped me to automatically trim and fluorescence trim these worms. So the fluorescence is very helpful to find targets in the resin, and there are specific protocols keeping the fluorescence during embedding. This is normally done by a separate fluorescence microscope, but of course it's time consuming because you have to transfer between the microscope and the ultramicrotome. And the trimming is actually done manually before you actually go to the ultramicrotome, but the block face creation itself is without a control. Now with the UC and UET, it's possible to observe the fluorescence directly on the ultramicrotome under room temperature and also under cryo conditions. Here you see the fluorescence version of the UC and UET with a mesa cut mirror here, the M205 stereo microscope and an orange protection cover. We mount the sample here and a 90-degree trimming knife. Here you see the mesa cut mirror, which allows us to look directly to the front of the sample. Everything is set up here before we start the automatic function. Filter cubes can be changed automatically here. And here you see a flow through chamber of the HPF in resin clamp with HM20. And when I switch off the fluorescence, you can see the worm appearing. Actually, this is the pharynx of the worm with a full front view by the mesa cut mirror. No osmium was used, so even with transmitted light, it's not possible to see the worm inside of this flow-through chamber. We pre-trimmed a little bit here, and this is now the cutting view. You can see the pharynx of the worm. And when we switch to bright field, you don't see actually where it is, just can guess. Then we do automatic trimming, like I showed to you before. The worm is here. And we define again the corners of the block face, the block face width, and the trimming depth and front face trimming depth. Now I automatically turn the sample to define the block face position, move the knife, and then we start the automatic trimming, a little bit of front face cutting. This is unfastened, of course, and I also skipped some of the steps not to bore you. Now the knife's retracting, sample is turning. Just to show you, the automatic trimming is also performed perfectly well under fluorescence conditions. And afterwards, you can see the little block face appearing here. There is the block face, and the worm is inside of the block face here. Switching off the transmitted light, you see the pharynx perfectly well. This block face in the top view by the Mesa-cut mirror, in the real front view, I mean, is a little bit roundish at one edge because this is the edge of the flow-through chamber. Here you can see this is the round edge of the flow-through chamber. It's not a failure in the block face cutting. And of course, we wanted to look quickly if we can see the fluorescence in the sections. We did some semi-thin sections here and switched to fluorescence to see if we can visualize the fluorescence also in the sections. And this was perfectly possible. You can see here the pharynx in the slices, in the sections. We picked them up on a slot grid. And here they are on the same fluorescence microscope. We could just see the pharynxes, the pharynx really nicely. So with the help of fluorescence, you can quickly identify your region of interest in a frozen or resin embedded sample. Perfectly here, the tip of the worm. This saves you time and of course samples by monitoring your sample fluorescence signal while trimming and sectioning. As I mentioned, volume EM and in particular volume SEM is becoming more and more important to create the 3D context of the sample. And there are several techniques available to create such serial block face images, and they all have in common that they are destructive. Here on the left-hand side, you can see that a knife is removing the knife, or a focused ion beam or a laser is removing the top surface of the block face after it has been imaged. But the slices, the sections are not collected. So it's actually destructive and the sections cannot be re-imaged. A better technique for this is array tomography. As I mentioned, we create these ribbons here on the ultramicrotome. It's non-destructive, and we collect the ribbons on wafers and put them afterwards into the SEM. Of course, there are obstacles like the uniformity of the sections has to be very precise for a correct rendering of the 3D data afterwards. And the ribbons must be collected safely. But with the UC and UAT, we provide to you the well-known technique by lowering the water level to collect the samples on the wafer. Okay, so how does this work? We mount the 84 knife, which hosts the SEM wafer. We connect here the valve for lowering the water level to attach the sections on the SEM wafer. You see here the holder for the SEM wafer after the ribbons are collected. And then we start the array tomography workflow. You see the block width is defined here. You can define the number of ribbons, the number of sections, and of course, the total number of sections is calculated. Then very important, we can define the number of release cuts which push the ribbons onto the wafer or open them for manipulation with the loop, for example. Then we define here the right-hand side of the knife for the outer alignment, because of course we can do an automatic alignment of this big knife, and it helps inexperienced users very much that this is done automatically. The system does the same as in the standard auto alignment, and the knife angle is defined here, the sample rotation and the sample tilt. This is done automatically. You see here the feedback lines. This is fastened a little bit. And now the system automatically goes to the right-hand edge of the knife. You can see it here appearing in the image, and does the alignment over the whole length of the knife. This is the left-hand edge of the knife. This video is unfastened. It takes some minutes, like in the standard auto alignment. After the sample tilt is done, you can finish directly or approach your sample, and we approached here and checked afterwards how is the alignment from the left to the right hand side. Good. Afterwards, we define the ribbon positions. The first ribbon position is here defined in the feed axis until the first full section is there. We start to prepare ribbon position 2 and 3, and then we go back to number 1 and start the sectioning. First full section of ribbon position 2 is done. Then click next. And then ribbon position number 3 is prepared. And afterwards ribbon position 1 again, right before the sectioning starts. We click next and start the sectioning. Of course, this is unfastened. First ribbon, second and third. And then after the third one is finished, the release cuts are done. Here in this case, we only took 2. Of course, we could push the ribbons onto the wafer, which you can see here below, but we wanted to save some of the material. That's why we just did 2 and released them by the loop. Then we had, of course, to manipulate a little bit that the ribbons are on top of the wafer. And then we carefully lowered the water level to attach the ribbons on the SEM wafer. Now we lower the water level. You can see they are nicely attaching side by side. And after it has dried a little bit and we changed the angle of illumination, you can see nicely how they sit beside each other here on the wafer. So with the UC and UAT, we simplify and speed up the serial sectioning by directly collecting the ribbons on wafers or glass slides, by providing to you the outer alignment of the AT4 knife, a guided software workflow, and a safe collection by lowering the water level in the knife. As mentioned in the beginning, we also provide everything for cryosectioning, and of course there are many challenges. The first one is to create the perfect cryo conditions, and this can happen in high humidity environments, which can cause ice crystal formation. For this, we can provide a cover for protection. We have to protect the sample by giving absolute control of the conditions inside of the chamber. During the sectioning, electrostatic charging may occur, and for this we have to provide electrostatic charge dissipation. Loss of ribbons can happen if you do not have a manipulator under cryo. And of course, if the sample is badly illuminated, you don't see properly inside of the cryo chamber. That's why we need a good illumination with multiple illumination angles here. And it can happen that you lose grids because you do not precisely manipulate them inside of the chamber. That's why we need manipulators under cryo conditions. And of course, we can provide this to you by first providing a cover which saves the samples under high humidity conditions. The control, the full control inside of the cryo chamber is given by different modes, standard modes, for example, for Tokuyasu methods, high gas flow to prevent ice crystal formation, and conditions for wet sectioning. We have sensors at the specimen, the knife, and of the gas entry, so you can really perfectly control the conditions inside of the cryo chamber. Full control also means manipulators and perfect manipulation during cryo conditions. Here on the left-hand side, the conducting fiber, and on the right-hand side, the manipulator for grids, for the grid take-up. Now let's have a look. During sectioning of a polymer, you can see the conducting fiber on the left-hand side is already attached, and we are moving it backwards during the cutting process. It's a little bit unfastened now. The ribbon is moving towards the observer, and the conducting fiber is moved by turning the micromanipulator manually. Here you can see the fiber in the center. And on the right-hand side, we now move with the micromanipulator the grid into position and charge to lower the ribbon on the EM grid. There it is. You can see the ribbon is attached to the grid now. The manipulator also can be used to load the grid then into the grid box. The cryo chamber is one part of the multiple upgrades we can provide to you. In essence, we can provide three different UC annuities for you: the basic, the standard, and the advanced. And you have the full upgradability to advanced features at any time. The compatibility with the cryo chamber is given for all systems. And of course, the well-known high mechanical precision, which you know from Leica microsystems. The UC annuity standard and advanced is compatible with all the high-end modules, which I showed to you today. And with the standard system, we introduce the motorized segment arc and the knife block, the motorized precise alignment, and the counters and presets, which I did not show today. The real outer alignment software function comes with the advanced system. The same applies to the automated trimming, and the camera is also only available on the advanced machine. The high-end modules, which I showed today, the 3D target plane trimming and the array tomography, the volume SEM, is available in the standard and in the advanced modules. For fluorescence applications, you need the UC annuity fluorescence. It shows the full upgradability to advanced features. It's compatible with cryo, so you can do cryofluorescence. The well-known high mechanical precision, counters and presets are available. A camera is needed, and standard filter set is delivered with the machine. The UC annuity fluorescence can be upgraded with the segment arc and the knife block to provide auto trimming. The automated trimming is then available with the segment arc and knife block being motorized, and it's compatible with the high-end modules for 3D target plane trimming and volume SEM. Take care, the auto alignment is not supported on the UC and UT fluorescence. So thank you very much for your attention. And if you have questions, please come forward and don't hesitate to ask your questions.
Thank you, Jan, for your informative presentation. We will now start the live Q&A portion of the webinar. Joining Jan will be Andrew Lawson, Product Performance Manager for the Sample Preparation Business at Leica Microsystems. If you have a question you'd like to ask, please do so now. Just click on the Ask a Question box located on the far left of your screen. We'll answer as many of your questions as we have time for today. Let's go ahead and get started. Our first question asks, do I have to use the motorized auto alignment?
Thank you, Cassie. No, you don't have to use the motorized auto alignment. You can also start with a basic system with the well-known manual micro manipulators for the segment arc and also for the knife angle, of course. Of course, if you have motorized a motorized segment arc and a motorized knife arc, you don't need to use it, so it's not mandatory. Yeah. Good question.
Wonderful.
Thank you.
Thank you, Jan. All right, our next question here asks, can you swap between the standard microscope and the fluorescence microscope?
Yep, I'll take that one. At this point in time today, there is not a pathway to swap the hardware between the standard M80 microscope and the fluorescence, the M205 microscope. That's something being worked on at the factory. It may come out sometime in the future, but at this point in time, there is no pathway to switch between the two microscopes. That said, if you plan to do any work with fluorescence, nearly all of the functions possible on the standard M80 setup can be done on the fluorescent system as well. The only thing really you could say is missing is the support for the auto alignment, as Jan mentioned.
Great, thank you, Andrew. All right, our next question that we have here asks, is this tool equipped with micro CT scanner?
Yep, I'll take that one as well. That's a great question. The UC Annuity itself, our Ultramicrotomy, does not have, it's not equipped with its own micro CT scanner. You'll need to use an external third-party micro CT system to generate your data first. What we do on the UC Annuity is import data from a micro CT system and manipulate that data, as Jan showed, to trim to a certain depth with certain orientation.
Very carefully, maybe I can add. Sorry, Cassie. We did some tests also with a confocal microscope to create data, because the UC Annuity software also can take standard Leica image files, and we did some pre-tests with a standard confocal using reflection and also fluorescence, and it worked quite well, although we did not check how precise we can be, because the refractive index of the resin is not corrected in any of these calculations. But we could really nicely see the sample, and we could do a target plane trimming, but the precision and the approach was kind of coarse still. But we are working on this, and in the near future, I hope I can write a little application note how to use fluorescence and reflection data from a confocal on our UC Annuity. Because I guess most of you have a confocal maybe in your lab, but maybe not a micro CT.
Excellent, thank you so much. All right, we're moving right along. We have a ton of great questions coming in. So please, again, if you have questions for our speaker or for Andrew, go ahead and submit them into that Ask a Question box, and we will try to get to as many as we have time for today. Our next question says, the microscope in your system, what is the maximum magnification?
I'll take that. We have, as said, we have two stereo microscope options. One is the so-called M80 stereo microscope, which is kind of the basic one. And then we have the bigger one, which is also used for the fluorescence part, which is called the M205. And this gives you a number for the ratio between the smallest and the biggest magnification. So the M80 has a ratio of 8 between the lowest and the highest, and it goes up to a magnification of 77. And the M205, so the bigger one, goes up to 160 magnification with a resolution of down to less than 3 micrometers. Yeah, that.
Excellent. Thank you. All right. Our next question here says, is the auto trimming and auto alignment functions can be used under cryo condition, or only one of each function can be used under cryo condition?
Maybe Andrew, you can comment on that.
Sure. Yeah, it's a good question. I would. The short answer is no. It is not possible to do auto trimming and auto alignment with the under cryo conditions. These motorized components are not compatible with the cryo chamber.
Okay, wonderful. Thank you. Moving right along, our next question here asks, what is the precision of the motorized segment arch and knife block? Is there any backlash?
Maybe I can comment on that. So we have precision of, I must look it up because it's so small, 0.05 degrees. Give me a second. I have to search for it. 0.75. Sorry, I have to quickly scroll through our tech specs. Still scrolling. Here. The sample tilt is 0.05 degrees, and the step size of the rotation is 0.1 degree. And I can tell you all the users which had hands on our machine were happy to have this precise movement of the motors. They're very quickly accustomed to using a knob, because you can just set the function on the knob, and you turn the knob very precisely instead of directly manipulating the segment arch or the knife angle. Yeah, so it's really precise.
Great, thank you so much. All right, our next question here that we have asks, can we use auto alignment with every diamond knife?
Maybe I can answer this, or Andrew, do you want?
Sure, I'm happy to.
Yeah.
So with the help of Diatome, we are offering a diamond knife guaranteed to work with auto alignment. It is an ultra grade diamond knife from Diatome. It's the auto knife, designed for auto alignment, to make sure that you have kind of the perfect reflection for the camera to perform this auto alignment. So that is the one knife that we can guarantee will work for auto alignment. That said, you are welcome to try the auto alignment with the diamond knives you may already own, with glass knives as well. And depending on kind of the properties of the individual knife, it may or may not work. So
Okay, great, thank you. Our next question here asks, can we use normal jumbo boats with Innuity AT?
Maybe I can answer this. This relates to the answer Andrew gave. So the big, you cannot, that's the short answer. But we provide the big 84 knife for auto alignment. And this is again, the edge of the diamond is made like that we can recognize it with the automatic image recognition. And yeah, perform the auto alignment.
Okay, wonderful, thank you. Our next question that we have here says, can a UC annuity standard basic system be upgraded to a fully motorized one with auto trimming option?
Sure, I'll take that one. The short answer is yes. The most basic UC annuity system that you can purchase allows for full upgradability with every possible additional function, minus the fluorescence at this point in time. So yes, with hardware and software upgrades that can be done in the field, a basic UC annuity can be enabled to do motorized auto trim, auto alignment, etc.
Wonderful, thank you. All right, our next question here says, what kind of resin do you usually use, and is the process complex for embedding the sample?
Yes, I'll take this one too. I saw this, I think, 1 or 2 questions along the same vein, so I figured I'd quickly answer. The type of resin you use really depends on your samples, your workflow, a number of factors. So it's hard to say specifically which resin you would or should use without knowing more about your work. But in general, the process for resin embedding is not too complex. It's very standard in the field, and it's well captured in the literature.
Great, thank you so much. All right, our next question here. We have a little bit of time left, so we'll try to get to a couple more. Our next one says, thanks for the presentation. What is the precision of the micro CT guided trimming? You showed an example targeting the head of a larvae, but what about aiming at a 10 precise window with an organ, for instance?
Maybe I can answer this. I cannot give you a super precise answer. So we have several factors in here. The first, of course, is the resolution of the micro CT. Typically, this is in the range of 1 to 3 microns or so. What I saw, but we could well get into the range of below this 10 micrometer. I would guess, because what we did, we approached this larva, and we could really go into a close approach from 1 to 2 micrometers. And I think if you have experience with your resin and with the machine, you can be very precise below the 10 micrometers very well. I hope this answers the question. It also refers to another question we had. Yeah, thank you. Good question.
Oh, sure. Yeah. All right, I'll go ahead and ask, I'll try to squeeze in 2 more here. This one says, hello, very nice presentation. Is there any possibility to use some accessories like knife support or sample holders, etc., from older UC6, UC7 in the new annuity?
I'll take that. Yes, your older chucks from the UC6, UC7 generation, older manual segment arcs and knife blocks should also work on the UC annuity.
Great. Thank you so much, Andrew. All right, we have time for just 1 more question. So that question says, hello. I'm just kidding. I was rereading, that was a duplicate. I'm so sorry. So that is all of the questions that we have time for today. So I want to thank you, Jan and Andrew, for your time today. We would also like to thank LabRoots and our sponsor, Leica Microsystems, for underwriting today's educational webcast. Before we go, I'd like to thank the audience for joining us today and for their interesting questions. Questions we did not have time for today, and those submitted during the on-demand period will be addressed by our speaker via the contact information you provided at the time of registration. This webcast can be viewed on demand. LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. Until next time, take care, everyone. Goodbye.